Our last episode introduced projection tomography. Among other strategies, we considered compressive sampling, where less than a full set of rays was used to reduce the overall dosage of an X-ray illumination system. How would we do this? Well, one strategy would be to use a coded aperture on the illumination side, which is what's done in this paper here from Gonzalo Arce's group at the University of Delaware. Today we're going to talk about how you design coded apertures for compressive tomography systems. Here's another example of a coded aperture X-ray system. In this case, the goal is to reconstruct along the path of an illumination source the molecular identity of the objects, which determines the scattering angle, and we also want to know the range to the object. In this case, we have an object consisting of aluminum at one range and salt at another range, and we get different scattering spectrum as what's shown at the lower left, and we need to design a code to disambiguate these things. So let's get into discussing how to design codes for projection tomography. Computational imaging. Episode 23, Coded Aperture Tomography. This figure illustrates a variety of different types of tomography and different ways of coding the rays that we use to illuminate a source or detect from a source. We have attenuation tomography, where rays are attenuated as they go through an object. We could have scatter tomography, where we try to reconstruct objects from the rays that are scattered within the object. We have emission tomography, where rays are emitted within the object. And for these different types of tomography, we can code the illumination and we can code the rays that we see on detection. As we saw last time, by using a subset of rays, we may get better image reconstruction per unit dose. There are other ways that we may try to use coding to improve the kind of estimation we can get in projection tomography. So today we'll talk about some strategies for doing that. Basically, we have a system as shown here. We have an object, we have a source. The source emits some set of rays determined by its physics, but we may want to use a coded aperture to code which rays illuminate the object, and then we can use coded apertures after the object to determine the direction of propagation of different rays. So this can be used in a variety of different tomographic systems. One that I mentioned in the introduction is coded aperture X-ray scatter imaging, where X-rays are scattered by the object. The scattering direction may indicate the nanostructure of the material, so we can use it to identify different materials based on their crystalline structure, but we need to know the direction of the scatter and the point to which the scatter came from. In the example in the intro, a periodic code was used. Here we see data from that system. Now what's going on here is we have salt at 60 centimeters away from the detector and aluminum at some 52 centimeters away from the sensor. The periodic code has the property that it's orthogonal with respect to scale. Earlier we talked about coded aperture imaging using modified uniformly redundant arrays, which have the property that they're orthogonal with respect to shift, which allowed us to form two-dimensional images. When we have an object at different ranges, we see the scale of the diffraction pattern changes as the range moves away. So using a code that's orthogonal with respect to scale allowed us in this case to identify the direction of propagation of rays in this circular pattern and reconstruct the spectra as a function of range as shown here. This is expanded in this fan beam CAXI system shown here, where we use a periodic array in one direction and a one-dimensional mirror code along the other direction to allow two-dimensional imaging. In this particular case, the system was set up with a fan beam illumination and then a two-dimensional code, and by analyzing the two-dimensional pattern, we're able to reconstruct the two-dimensional slice of the image in a single snapshot. So here we are at the lower left, there's measured data from this code, and in this case, the object consisted of a phantom of various materials, where a slice through the phantom was reconstructed in a single snapshot. The snapshot imaging was illustrated here, where we put an alarm clock in the X-ray system, and you can see that the second hand of the alarm clock was reconstructed in single snapshot images, which had allowed temporal imaging of the motion of the alarm clock. In the text and in the GitHub repository, there's a particular design example to allow you, the reader, to explore the design space of coded apertures and coded aperture imaging for X-ray systems. In this case, it's a compressive coding system. We have a two-dimensional object. Here's X and Y. and rays through this two-dimensional object are going to pass through the coded aperture on their way to a detector array. So we need to design the coded aperture and a reconstruction algorithm to try to estimate the two-dimensional object from a set of measurements along a one-dimensional detector array with a one-dimensional code. Here's the GitHub repository where this is evaluated, so I encourage you to go there and check out the code. In this case, we choose, for example, a random code. We're going to make 128 measurements with our code, and we have 128 coding elements, but the object is going to be 28 by 28, so there's 700 and some object voxels. So our forward model is we have our two-dimensional object, and we're evaluating measurements as a function of one dimension. We're labeling the longitudinal direction Z, and so we have this scaled version of the code according to the same models we used in coded aperture imaging for reconstruction, but now we're assuming we're reconstructing as a function of transverse direction and range. So if we think of our object space and a detector element here, going through the code, we have some visibility. And so if through the code, these regions are visible, then they're coded with something proportional to the area that we see from that region onto the code. And we do that through each one of the coding elements, and we can develop a forward model. So this is a model of the 128 measurements along the vertical axis and what their visibility is for each of the 700 and some resolution cells in our 28 by 28 image. So this is a model for each one of the resolution cells laid out in raster form. We can look at the sensitivity of each one of the pixels. So this is the which regions of the object. So with each pattern here we show is a pattern over object space, and bright means that pixel is seeing that voxel in the object, and dark means it's not seeing it. So there's a mask that's overlaid the two-dimensional object for each pixel. So the sensitivity of each pixel tells us what we're seeing in each pixel. We can take the forward model and look at the singular vectors of the measurement space. Now in this case, because the code is on one side of the object, we have higher resolution features close to the code and lower resolution as you go away from the code over the object. So our features are not uniform in spatial scale over the object space. But these are the features we see in singular vector analysis of the forward model. We could rotate the code to different directions or rotate the object if we wanted more symmetric codes. But now this is a compressive measurement system because we're taking 128 measurements and we want to reconstruct 700 and some object voxels. In the GitHub code, this is implemented as a test example with the minced digits as objects. So the top row is the ground truth of some set of digits. The middle row is what happens if we reconstruct using algebraic reconstruction, like we talked about in the last lecture. And of course, the algebraic reconstruction shows artifacts because of the unstructured form and the compressive nature of this measurement problem. But the bottom row says that we're going to use an autoencoder neural network operating on the algebraic reconstructions to try to recover the original object, and it does a reasonable job of that. This is an exercise whose main purpose is to allow you to think about how to analyze a code, how to look at the singular vectors, and then how to do reconstruction. Of course, this is kind of a toy problem. In the real examples, you would use the code and the design in an iterative form to try to optimize overall system performance, and you may be interested in things like orthogonality of codes as with the harmonic or mirror codes and other sorts of non-algorithmic ways to evaluate the quality of the codes, including looking at the structure of the singular vectors. So that's an example of coded aperture imaging. Next time we're going to talk about details of actual projection imaging systems. This is an example of a two-dimensional detector array. This has 99 micron pixels for X-ray imaging, where the wavelength of the X-rays is going to be something closer to the nanometer or angstrom scale. So one wonders why use 99 micron pixels, and that will be the topic of our next discussion.